How do we go from overall system design requirements to an actual design? This happens through a guided and iterative decision-making process that allows us to put details on our design. I say guided as the process is not rigid, but rather there are some guidelines that we use together with our ability to be creative, find information, and think critically. To be able to do the design, we follow 4 basic principles. First, we work from general to detail. Next, we think in variants by consistently looking for alternatives. We follow a phased approach where the development is subdivided into sensible and manageable chunks so that it is possible to verify that things are on track. Finally, we apply problem-solving processes and logic at each stage to be able to make decisions, and we document how those decisions are made. In the design, we go from general to detailed until we arrive at the level where we have specific parts with specific attributes such that we are either able to buy them or make them. As you move through levels of detail, the questions to ask are, what are the variants possible at this level to deliver what is required? These variants may be wildly different things, or they could be minor variants. We are most concerned with major variants initially. Then we ask, can we decide amongst these variants, or do I need to go to more detail? If a decision cannot be made, that is no trouble. It is part of the iteration process. Finally, we need to decide or specify anything at this level before moving to the next level. Variants are not all made the same. Significant variants are clearly differentiated by some basic idea and have distinctly different major features as a result. It is desirable, but not always possible, to make early decisions on significant variants to save work on completely different variants that impact lots of other things. Details variants, on the other hand, are based on the same basic idea, so have similar major features but vary just in the details. These have less impact on the design and are often not decided in the early stages of a design process. For example, looking at the literature on solar power, there are 2 major subsystems to a solar plant: solar energy conversion and treatment of electricity so it is ready for the grid. From the literature, there are 2 major variants for solar conversion: photovoltaics and concentrated solar thermal. These are completely different systems with very different technologies and layouts. So these are significant variants that would be good to decide now which one to use. The choice directly impacts overall system performance, so I can use system constraints and objectives to choose between these 2 variants. Using information from the literature, I can determine if these technologies can meet constraints. Note that I've had to use references in several places here to source information for this to be able to support what I am saying. When making the comparison, we always use constraints first. If a variant cannot meet a constraint, they are rejected before using any weighted criteria on objectives. For this system, there are a couple of key constraints. The first is to be able to produce electricity at the required capacity of 100 megawatts. Both technologies have existing facilities in the world that achieve that. The next is, for this capacity, the plant has to cover less than 400 hectares, which is the amount of land available. Both these options meet the requirements. Given that these have met the 2 key constraints, we now must compare them on the basis of objectives. To be able to decide between objectives, we will use a weighted decision matrix. To be able to use that, we need 2 things. The first is that we need to decide the weighting of the objectives themselves. The second is that we need a scoring system for how well a variant meets an objective. Once we have these things, we can use them in a decision matrix. Here we see a pairwise comparison table for the objectives for the solar power system. To get the raw weights, we divide the sum of a row for an objective by the total across all objectives. For lower total cost, the weight is then 5 divided by 15 to get 0.33. This is repeated for all rows. Once this is done, we fiddle with the weightings a little so they are neat and reflect more closely how we see the weighting. For example, lower land use should have some weight, even if it is behind the other 5 objectives. These numbers should indicate the relative importance of each objective in decision making. Next, we need a scoring system for the variance to be able to use these against objectives. The most important thing is to be consistent and clear. It is recommended you use a simple 1 to 5 scale, where 5 is the best amongst the variance and 1 is very poor performance that is a long way behind the best available. We generally want to use whole numbers so that things are clear and we don't have to spend too much time fiddling with small differences. As a general rule, 0 should never be a score given. This would indicate that an unrealistic variant has been chosen, or that what is listed as an objective is actually a constraint that should be added to the constraint list. To put a score against something, you need to know something quantitative, for example, a maximum speed, or qualitative, for example, it's visually appealing, for that objective for that variant. Quantitative scores can be directly scaled and rounded to the nearest 1 or 0.5. If something is twice as fast and this is desirable, it might have twice the score. Qualitative scores require some commentary to make sense, but fundamentally should give an idea of how close options are on the scale in your view. It is the relative score between variants that is important. Applying to the solar generation options, we see that the solar PV comes out a long way in front. It is the better option across all criteria except for grid stability, given that concentrated solar thermal plants are able to modulate their electricity export. On all other objectives, solar PV performs better and has a score of 5. This leads to an overall score of 4.55 versus 3.5 for the concentrated solar thermal. This process is repeated iteratively down through different levels. You can generally only make decisions at 1 or 2 levels of detail before having to verify that these combine to produce the desired outcomes for the system above. Decisions at lower levels may mean that you need to iterate design requirements and decisions at higher levels. Each new subsystem has its own requirements. These can be inherited directly from or modified versions of the system constraints and objectives, or new requirements that come from other subsystems and how they interact in terms of functions, connections, and layout. For example, the weight of one component may translate into a constraint for the design of another component that has to bear that weight. As you move through levels, it is common that you cannot decide between options. This indicates that more detail is required, and this greater detail may come from a lower level. That is okay. Simply note what sort of information you are missing that you would need to be able to make a decision. At the conceptual stage, it is common to have to consider several variants in more detail or leave them for a later decision when they do not have much impact. An example of a system that has to be designed after other things is the mount system used for solar panels. After making several more decisions, like whether the solar panels are fixed or tracking, one will finally arrive at the mount system. The design of the mount system will have new constraints due to weight and other structural considerations that come from the panels themselves. For the mount, only 2 objectives carry down from the overall system requirements to this subsystem. These are that we still desire a low-cost solution and that ground disturbance is minimized. The latter objective has become much more important for this subsystem in comparison to its importance for the overall system. The actual design of this system can only come after most of the other aspects of the solar panel have been decided and designed. Now that we've gone through an example of how this works, we can see that as we move through the design, we gain more and more detail. The way this works can be considered a spiral, where we are making design decisions on subsequent levels. Each time we have to consider the requirements for each subsystem we come across. Each time variants are proposed and evaluated. This is referred to as a spiral design. Whilst not completely accurate for all situations, it is a good way to think about designing systems. We can also see that this continual set of design cycles is part of the V model of design. This diagram shows quite clearly the very important iterations that need to happen as you move from one design stage to the next. But in each stage, you have design, analysis, requirements, and then iterations between stages. Design is an exercise in decision making. By breaking the design into bite-sized pieces and approaching it systematically, we can design a system that initially can seem very complex and impossible to tackle. But by breaking it down, it is possible to achieve a design outcome.